Alright, what's going on everybody? Today we're doing another LeetCode video. This one is called Permutation in String. Hold on, I forgot to make this full screen, so let's do that. Alright, so yeah, it's a medium. We'll be solving it in C++. Let's get into it. So we're given two strings called S1 and S2, and they want us to return true if S2 contains a permutation of the first string, S1, or false if otherwise. In other words, return true if one of S1's permutation is a substring of S2. So what does that mean? It's basically we're looking, so S1 is going to be our first string, our smaller string. Well, it should be smaller. It's actually the first thing we'll check now that I think about it. Just kidding, I already knew that. But basically, if S1 is bigger than S2, there's no way it can be in S2 at all, because we're looking for S1 and S2, but not just in order. It can be in any order. So what does that kind of sound like? It kind of sounds like an anagram, right? So an anagram of S2, we're basically looking for an anagram of S1 and S2, right? I think an anagram, right, yeah, it's not a palindrome. Palindrome is the forward-backward one. Anagram is just comprised of the same characters. So notice that this one is true because AB is in here as BA. And it's got to be intact, remember, S1. Like so for this example, we have AB, but the B and the A are separated. Obviously, like that doesn't count. They got to be together still. The string's got to be intact. Just it could be in any order, so hence permutation, but it can't get split up. That's so this is false. S1 and S2 can only be lowercase English letters. So that's important because instead of a regular hash map, we can actually just use a C array, which is quite a bit faster for our algorithm, because we're going to be a key component of this, by the way, is going to be to count the frequencies, kind of like you do for an anagram problem, or pretty much exactly like you do for an anagram problem. So to make that really efficient, we can use C arrays, since it's just going to be those 26 lowercase English letters for our keys. But anyways, yeah, I mean, that's about it for the problem introduction. We can go ahead and get into the code. So into the solution. So this solution is a bit longer, so I'm gonna have to remember to zoom out as I go, because yeah, the code's gonna get to be a lot. So nevertheless, the optimal approach here is going to be to use a sliding window and char frequency maps. Okay, and then basically what that means is we're going to have a sliding window of fixed size. It's going to have size of S1. We're just going to traverse it across S2 and see for at every substring, or at every substring in S2, is that a permutation of S1? So that's pretty much the solution. And I'm going to show a really optimal way we can do that. So the time complexity for this method is going to be for the solution I'm going to show, because there's like different ways you can not optimize this well, but I'm going to try to optimize it as well as I can. So the time complexity is going to be linear, basically with respect to S2, because we're sliding a window across S2. Well, I guess, and S1 kind of. You'd have to slide the window less if S1 is like closer to the size of S2. But nevertheless, linear time respective to those input strings, and then the space is going to be constant, because the data structures we're using are just character frequency maps, which obviously are going to have 26 elements. Always doesn't matter what the input strings are. So yeah, time and space, sliding window, character frequency maps, linear for time, constant for space. So let's go ahead and get into the code. So the first thing we're going to want to do is declare those character frequency maps. So, well, we're going to need a map for S1, which isn't going to change after the first time we count the frequencies, right? Because that's kind of just the goal we're looking for in S2. All of those are going to be 0 at first because we haven't populated it yet. And then we also need a map for S2. It's not going to be containing the frequencies for the entire string. Remember, the map for S2 is just going to be whatever substring is currently being examined. We also need matches count, which basically there can be up to 26 matches. It'll be 0 at first, and that just corresponds to every single character in the substring in S2 and in the S1 map. our every single character has the same frequencies, at which point we can return true. So that's going to be 0 at first. So we're going to be monitoring that matches count and then updating these maps as we go. So let's go ahead and populate those frequency maps at first. So we can just do a C-style for loop and basically just loop through the first string, the length of the first string, and then basically, let's see, and basically, we just want to index into the first map first, and then to normalize that to 0 with -a. And I've explained that in a lot of my other videos, but basically what this part of the code is doing is making it so that so like this converts to an integer automatically, but it's not going to be 0 indexed for A. So by doing this, we're making it 0 indexed. B would be 1, C would be 2, etc. So we're doing that, and we're going to increment the frequency of that character in the first map. We need to do the same thing for the second map. And this is going to be in string S1, and this will be in string S2, because we're counting the frequencies for those respective characters in the respective strings. So that just initializes the frequency map. We also need to initialize the number of matches. So we can just iterate through those 26 indices, because those frequency maps are going to have fixed size, like I was saying before. So, and then just to update the matches, if the character frequency in S1 at I is equal to the character frequency in map S2 at I, then we increase our matches. So that's pretty much it for the setup for the problem. Also, one thing we have to do first is remember, if S1 is if the length of S1 is greater than the length of S2, like there's no way that can be inside of like there's no way a permutation of S1 can be inside of S2 if S1's bigger, right? So like we just have to return false there. It's pretty obvious, but that's like an important edge case. We have to get that out of the way first. So at this point, we're pretty much ready to implement the sliding window. So let's go ahead and do that. So we're gonna need a left pointer that can be 0. Remember, the sliding window is gonna have a fixed size always, corresponding to the length of S1. So the right pointer can just be S1.length. And then let's see, I think that's all we need for the stuff before sliding window. So then we're basically gonna just loop while the right pointer is less than the length of the second string. And we're going to, what we could do is just update we're going to be incrementing the left and right pointer every time, no matter what. So let's just get that out of the way. Also, if our matches at any point is equal to 26, we know we've found a permutation in S2, so we can return true. And at this point, we want to basically see how we adjust our frequency maps. Now you might be thinking, every time we switch every time we adjust the window in S2, like how are we going to update our frequency map? Well, if you take a look at, so let's say we're looking at a window of length 5 here in S2. Now, what happens when you shift this window? So if we went from this window to this window, notice all we're doing is just adding a character to the frequency map and then subtracting a character from the frequency map, essentially, as we are shifting the window down. So that's all we have to do. We can just hard code for that and then update the matches every time by checking, basically comparing. It's like, okay, we just changed one of the characters, so let's look at that character and see if the matches like changes. So we're gonna need to index to make this code a little bit make the code a little bit nicer. So we can say, and this will be the index we're using to get into our map. Actually, I don't really like index. We'll call it a key. So this will be key, and the key will be, because it's going to correspond to a character, really, but 0 indexed. So this is going to be S2 for a right pointer, and to normalize that, we'll just subtract A. And then what we need to do in our S2 map is, remember, for a right pointer, we're adding a character. So S2 map at our key plus plus, and then we're going to need some conditionals. So basically, we just added a character to the frequency of S2 map at key. So we need to see if we just gained a match or if we just lost a match. Now, how do we know if we gained a match? Well, we can simply compare those two maps at that key. So S1 map at key, if that now equals S2 map at key after we changed the frequency of S2 map at key, we know our matches is increasing because we just went to from not a match to a match. Now, how do we know if we went from a match to not a match? Well, we can't just see if they're not equal because it might have not been a match before. So we need to basically say if S1 map at key plus 1, because we just added 1 to S2 map, if that plus 1 equals to S2 map at key, then we know we just went from a match to not a match. So we can decrease our matches. And we're going to be doing the exact same thing basically for the character at our left pointer. Not really the exact same thing. It'll be a little different because we're losing a character. So we're changing that index into S2 to be our left pointer. We're going to subtract it from the character map because remember, we're losing that character. And then this is going to be the same because if they become equal after changing this one, we know we are going from not a match to a match. For this, it's going to be different because we just subtracted from this. So we're just going to change that plus sign to a minus sign. So basically, if this one now is equal to this map at that character after we subtract one, then we know we went from a match to not a match, so we can decrease the matches. So that's pretty much it for the code inside of the sliding window. Now, technically, we still haven't checked, and I'm going to zoom out even more because there's a ton of code here. So technically, we still haven't checked the last substring in S2. So like for this example, say we didn't find this substring here. Let's go to this example since technically we still haven't checked these last two the matches for these last two substrings. Like we've already calculated or tallied up the frequencies, but we just haven't checked the matches. So to account for that, instead of just returning, because like otherwise you would just return like false here, but we actually have to check if matches is 26 first. So basically we could do a little ternary thing here. So if matches is 26, then we can return true. Otherwise we'll just return false. So that's pretty much it for the code for this problem. I'm just going to scan over this quickly to see if there's bugs. There's a lot of code here, so I wouldn't be surprised if I made one. So redefinition of key, right, yeah, so that's like a little bug there. We cannot redefine key, but we can use the same variable, which is kind of what I was getting at. So let's go ahead and run this again. So accepted those initial test cases, so I think we're good to go here. So again, I mean, it's going to be linear runtime, constant space. So these are the percentages. You can probably play around with those and get a little better. But yeah, I hope this video helped you understand this problem more. If it did, like it, subscribe, run it up, and I'll see you guys in the next piece.